From this lecture, we will start to introduce the concept of one-to-many systems. A general one-to-many systems can be very complicated. To start simple, we consider some fundamental building blocks. The first one we will introduce now is traveling salesman problem, or abbreviated to be TSP. So the traveling salesman problem is that if we want to travel a certain amount of cities, we want to find a tour that we can visit all the cities and return to the point of the departure, and we want to minimize the total distance. Here, the distance can be its physical distance. For example, you can use Google Map and then search from one point to another point what's the minimum travel distance, or the minimum travel time, or some other cost related to the traveling, for example, the air tickets. So typically, how should we model this type of problem? We will introduce mixed integer programming. We will introduce some notations. Let's see, we have n cities, and then we have all these cities with index from 1 to until n. And then between any pair of cities, for example, city I to city j, all belong to 1 to n. So we can find out the distance from city I to city j. This is our parameter called Cij. So our decision would be Xij. It's a binary decision variable. It can be either 0 or 1. So if it is 0, we say that I does not travel to j. So if Xij is 1, we can say the next step from city I in the travel is to city j. If we just use Xij to indicate all the possible decisions, there are some issues. Because we visit all the cities and then go back to the original departure point, to indicate the order of the city in the tour, we define yi to be the sequence of our visit. With these integer decision variables, we can easily calculate the total cost for the travel, or total distance, which is just summation over all ij, xij times cij. This is intuitive. If you travel from I to j, you add the cost or the distance from I to j, cij, to your total travel cost. Otherwise, you do not add the cost. There are a set of constraints we need to consider. First constraint, you need to guarantee that you go to a city and then you need to go out. So this typically we call it conservation law. If you go to a specific city I, let's say from some other city j to some other city k, so that indicates for all possible city j to city I, given all j, this is equal to 1. So that means there must be one tour from certain city j to city I. On the other hand, we have one city go outside for all possible choices. So the next constraint, which is call it subtour elimination constraint. So for subtour elimination, we will just guarantee that the city you visit are in a certain order, which we can denote them by y. So for example, without loss of generality, we assume the tour starts at city 1 because y is our sequence in the tour. y1 equals to 1 indicates our first step in the tour is in city 1. And then we want to guarantee that if xij equals to 1, then we hope that yj should be greater or equal to yi plus 1. Because all possible y values from 1 to n, if we can satisfy this constraint, that indicates the sequence to visit city j must be later than city I. So for example, if you have 3 cities, and then we have the TSP tour from 1 to 2 to 3, and then back to 1. So we know like y1 is 1, because here we have a step from 1 to 2. So we know x12 equals to 1. So this indicates y2 is greater than y1 plus 1. And then similarly, we know x23 equals to 1. This tells us y3 is greater than y2 plus 1. And then when 3 goes back to 1, because 3 is already the last step, so we need to guarantee that here we need to exclude j is a starting point. So we do not have any constraint if we return from a certain city to our departure point, city 1. Because y can only take values from 1 to 2 to 3, and y1 is 1, y2 is greater than y1 plus 1, and y3 is greater than y2 plus 1. So this tells us y1 equals to 1, y2 equals to 2, and y3 equals to 3. So let's use another example to show a subtour. For example, 1, 2, 3, 4, we have 4 cities, and then we have a TSP tour from 1 to 2 to 3 to 4. And then a subtour means you can go from city 1 to city 2, but then you directly go back. You can start from city 3 to city 4, and then go back. So here you can see in this subtour cases, the conservation law is satisfied. For any city, only one tour goes in and only one tour goes out. So there's no violation on the conservation law, but it's definitely not a TSP. That's why we need to introduce the order, because when we have the order, we know that the sequence is 1, 2, 3, 4 in the tour. But if there is a subtour, similarly, we can have 1 and 2. Then when we have this label, you can see if we assume the sequence is still 3 and 4, there will be a violation because x34 is 1. So that indicates y4 should be greater or equal to y3 plus 1. And then because x43 is 1, then that tells us y3 has to be greater or equal to y4 plus 1. Here, 3 and 4, none of them are the starting point. So that indicates a contradiction. y3 has to be greater than y4, and y4 has to be greater than y3. There's no solution. This is infeasible. So introducing the sequence in the tour can eliminate the subtour cases. Now let's see how we can convert this condition into constraints. So here we give its equivalent formulation by the following. Okay, so this is a very interesting reformulation, and here is the number of cities. This formulation converts this if-then condition into a constraint. Let's see why. If xij is 1, then the above formula will become yj greater or equal to yi plus n minus n minus 1. So this is equal to yi plus 1. So this is exactly the expression we like to have. On the other hand, if xij equals to 0, then the above constraint becomes yj is greater or equal to yi plus 0 minus n minus 1. So you know, like the range of y is from 1 to n. So the right hand side is at most 1, maybe negative. So that always holds if we guarantee that y are chosen from 1 to n. So that means there's no constraint on the choice of y value when xij equals to 0. So in summary, we can formulate our TSP in the following ways. We minimize the total distance L for all ij as our decision variable if we travel from city I to city j with a cost ij. This is for all possible I and j. And then we have the following constraint. So any cities to I, summation of the decision variables should be 1. That indicates we have one path to city I. This is for all city I. And then we have the symmetric properties. We have to guarantee that only one path going outside of city I for all possible I. Sometimes we can write these two constraints together for notation convenience. So, and then this is our subtour elimination constraint. Remember that we guarantee this is for any I and then exclude the starting point. And then our starting point is assumed to be 1. Here, actually, we do not need to assume y1 is 1. We can assume y2 is 1 or y3 is 1 doesn't matter. If you assume y2 is 1, then j be not equals to 2. Or if y3 equals to 1, then j would not equal to 3, based on our starting point. So in general, we can write into ys is 1, and then s is our starting index. Doesn't matter. So without loss of generality, we normally assume y1 is a starting point. Okay, and then definitely our xij are integer, and then yi are from 1 to n. So this is our optimization problem. This variable is xij, yi. This is our conservation law. This is our subtotal elimination. And then this is our integer decision. So we can write out all the decision variables for a possible example. Let's see, we have a tour from 1 to 3 to 4 to 2, and then go back to 1. Okay, so that can give us decision variable. Let's see, I is from 1 to 3, 4, and then j is 1, 2, 3, 4. So this can tell us our first step is from city 1 to city 3, so this is 1. Second step is from 3 to 4, 3 to 4 is 1, and then 4 to 2, 4 to 2 is 1, and then 2 to 1, 2 to 1 is 1, so the rest are 0. So you can check every row, the summation should be 1, and every column, summation is also 1. And then our sequence for yi, because this is 1, 3, 4, 2, so the sequence should be 1, 3, 4, 2. So that's our sequence.